So hello everyone, welcome to today's live interactive session on geology and soil mechanics. So as you all know, today is the ninth week of these discussion sessions, and so already 2 months of discussion sessions are over, and with today's lecture we begin the third month. So today onwards from 9th, 10th, 11th, 12th we are going to have 4 lectures of 2 hours each, 9th, 10th, 11th and 12th, and after that we are going to have a 13th lecture or a summary session for of 1 hour. All right, so uh, let us start today's session slowly. And before that, if you remember, if you recall, in the previous week, what we studied was we studied about the shear strength of soil. We studied about the what to say, the triaxial test, various types of triaxial tests, and then what we did, we solved some problems regarding all those things, right? So in today's session also, what we are going to do is that we will be um, revising a bit of from this triaxial test topic. We'll be seeing some more intricacies of the triaxial test topic, and then we will be seeing what are stress paths, right? We will be seeing what stress. So we'll see that. After that, we will be solving a few problems, not many. We will be solving 9 or 10 problems regarding this test and all other things. Okay. So with this, probably we are going to end the shared strength topic, and in the next session, we are going to start with something new. Okay, something else. So let us start slowly. All right. So let us start one by one. Let us see what is there for us in today's session. So we discussed about the tests, right? We actually studied in detail about the test, like the CD test, the CU test, and the UU test. So some more parameters related to this triaxial test that are very important and we should know about them. Those we are going to discuss in today's session. Alright, those we are going to discuss in today's session. So these parameters are actually called the Skempton pore pressure parameters. So there are two parameters A and B, and these two parameters are called the Skempton pore water pore pressure parameter. Why they are called pore water parameters? That is because they give us some relation to the pore pressures that are going to develop while load application. So that's why they are called the pore pressure parameters, and we are going to see what those, right? So the first okay, so if we recall, uh, what is CD test? So in CD test, if you remember, so C means consolidated, D means drain. So in the first stage, we are going to consolidate the sample, and later in the second stage, that is in the shearing stage, where we keep on increasing the axial load or the deviatoric stress. What is going to happen? The shearing of the soil sample is going to happen. Okay, in that shearing stage, what we are doing, we are keeping open the drainage valve, and due to that, the pore pressure dissipation is going to occur. All right. Okay, so what happens is that first, in the first stage, you consolidate the soil sample, and then in the second stage you start shearing, right? So what you get? So you get some what to say, some more circles like this, right? You get some more circles like this. So, and then you draw a common tangent to the mode circle, then you draw a common tangent to the mode circle, so that will actually give you the phi and the C, that is the friction angle and the cohesion. And as the test is CD, that is always going to be our what, that is going to be the effective parameters. Okay, so phi prime and C, Fine. Okay. Okay. And this is nothing but the filler envelope. All right. Now, this B parameter that is written here, the B parameter. This B parameter is the parameter that we get from the first stage of a triaxial test. That is, we get this from the consolidation stage of the triaxial test. So what is B? B is equal to UC by sigma 3. That means UC is what? UC is the pore water pressure. Okay, increase in pore water pressure, or the pore water pressure, excess pore water pressure that gets generated on the application of sigma 3, or on the application of a cell pressure, right? Or the cell pressure. So as we apply cell pressure, what is going to happen? The pore water pressure is going to increase, isn't it? So what we are going to do is that we are going to measure this ratio. Say uh, uh, first sigma 3 was sigma 3 1, then you are changing this sigma 3 to sigma 3 2, increasing. So now this change in, or this pore water pressure, this extra amount of increment in the cell pressure that you are giving, all that should actually get reflected as the pore water pressure. Okay, then only what will happen, if all the extra increment of cell pressure gets reflected as the pore water pressure, then what will happen? This ratio is going to be 1, right? So if the ratio becomes 1, then we will be able to call the sample completely saturated. Okay, so that's why it is written here B is equal to 1, approximately 1 for saturated soft soils, but for steep soil B can be less than 1. Okay, that means you apply cell pressure and we note down the pore pressure. Okay, then we increase the cell pressure, and that increment in cell pressure should reflect as equivalent increment in the pore water, as a pore water pressure, right? But that will only happen, that will only happen when the soil is perfectly saturated or completely saturated, right? That's why B is approximately equal to 1 for saturated subsoil, but for steep soil B can be less than. Okay, for generally, for completely saturated soil sample it is very close to 1. So when we do the triaxial testing, before starting the consolidation, what we need to do, we need to ensure that the soil sample is perfectly completely saturated. All right, so what we need to do, before we start the consolidation process, we need to ensure that the soil sample is perfectly saturated. So how do you ensure that the soil is saturated? We ensure it by checking the B parameter, or calculating the B parameter. All right, we keep on checking the B parameter, and that B parameter actually gives us an idea whether the sample is perfectly saturated or not. All right. Now there is one more test we studied, that is the CU test. Okay, the CU test means consolidated undrained. Here in the second stage, this is in the sharing stage, the drainage valve is actually closed. So as the drainage valve is closed, during the sharing process, what is going to happen? Extra pore water pressure is going to get generated, right? Extra pore water pressure is going to get generated. So that is how we define the parameter A. So here you can see A bar is equal to change in pore water pressure by change in the deviatoric stress. So you are increasing the deviatoric stress, and with that increment you are seeing how much increment in your pore water pressure is actually coming. Okay, so we are measuring how much increment in pore water pressure is actually coming. Okay, so pore water pressure increases by delta UD on increasing deviatoric stress delta sigma D in the second stage. It is in the sharing stage. So why CU test is sometimes referred over CD test? Because as the CD test the shearing stage is a drain shearing stage. There what we have to do, we need to apply the load very slowly so that excess pore water pressure does not develop. So that's why the test is very slow. That's why sometimes we prefer the CU test instead, which is much faster than the CD test. But in the end, everything depends upon the engineer, how, where you are going to use, where you are going to actually going to use the values of CN5. That depends on what scenario you are going to use the CN5. That depends on what test you are going to do. That is going to be undrained test or it is going to be drain test. Okay. So we see here that at failure A change A we put AF means A at failure is nothing but the change in pore water pressure at failure by David change in David stress at failure. For NC clays the AF varies from zero point 0.5 to 1, and for OC clays the AF, that is the over consolidated clays, the AF varies from minus zero point 0.5 to 0. Why this minus in terms of over consolidated clay? Because say if we plot the volume, the change in volume, original volume by the with the shear strain. For normally consolidated or you plot uh, for normally consolidated soil, what is going to happen? The volume is going to reduce. As you increase the shear strain, the volume is going to reduce. But for over consolidated clay, first you are going to have a reduction, but then what is going to happen? The volume is going to increase. That is there is going to be a dilation. For like there is going to be a dilation. So due to this, what happens if you draw the pore water pressure? So due to the reduction in volume, this is for NC, so OC. So we have positive pore water pressures that get generated in NC. Okay, but in case of over consolidated clay, first we will have positive pore water pressures. After that we will have negative pore water pressure. Okay, so that's why for over consolidated clay we have AF negative, varying from negative. Okay. All right. Same. This is for normally consolidated clay or loose sand or dense sand or loose sand. Okay. Now UU test. So UU test is what? Unconsolidated undrained. So we do not consolidate, neither do we consolidate, neither in the second step we open the drainage valve. So drainage valve is closed in both the stages, in the first stage also in the second. So directly after putting the sample, we apply some cell pressure and we start the shearing. That is the unconsolidated undrained test. Okay, unconsolidated undrained test. So as soon as you apply the cell pressure first, as soon as you apply the cell pressure, what is going to happen? Some pore water pressure is going to get generated. Their pore water pressure is nothing but the UC, and then when you are start applying the David stress, again some pore water pressure is going to get developed. That is nothing but this. Okay, so UC is due to the application of sigma 3 or the cell pressure only, and delta UD is the application from the David stress, right? Now UC we can write. Now UC we can write B into sigma 3, right? We saw that B is equal to UC by sigma 3. So UC you can write B equal to sigma 3, and delta UD you can write A bar into delta sigma D, right? So total increase in potential pressure is nothing but UC plus delta UD. So you can write B sigma 3 plus A bar into delta sigma D, right? Now this deviatoric stress, okay, this deviatoric stress with that increment, that we can write nothing but sigma 1 minus sigma 3. The deviatoric stress is nothing but sigma 1 minus sigma 3, right? So that we can write as sigma 1 minus sigma 3. Okay, so this is the expression for the total pressure. So delta sigma D you can write as this is minus 1 2 just ignore this. Okay, we'll leave it. Just I was just thinking something else. Okay, just leave it. You'll see this. Okay, so this is all. The next is the UCS test. What is the UCS test? You already know that unconsolidated, this unconfined compressive stress. So here what is there? So in UCS test we have sigma 3 is 0. So we get a circle like this. This is nothing but the UCS value Q. Sorry, this is the C. Okay, and this is the Q. Okay, and what will be this? This will be equal to QU by 2. Okay, C is equal to QU by 2. This we already know. We already saw this in the previous class, right? So what is UCS? Directly of the sample, we keep on applying this sigma 1. Okay, okay. Nothing much is there actually here. Already we have discussed all these things in the previous session. Okay, now let us come to the new topic that we are going to introduce in today's session. That is the stress path. Okay, there is the stress path. So what are stress path? Okay, what are stress path? Let us see what stress path are. The locus of the points representing the stress states during the progress of a test, that is nothing but the stress path. The locus of the points, it is locus of some point. Which point we are going to see? Locus of which point we are going to see that. The locus of the points representing the stress states during the progress of a test. Okay, locus of the points representing the stress states during the progress of a test. Okay, so that is nothing but our uh, stress path. Okay, our locus of which point we will see. So q prime p prime plot is generally used. And what are q prime p and p prime? q prime and p prime actually represent the coordinates of the top of the Mohr circle. That is, right, right. So what is sigma 1 plus sigma 3 by 2? It is nothing but this point and this point, right? So this is p and this is q. So this coordinate of the diametrically opposite point to the center, right? So this coordinate of this point is nothing but p prime q prime. Okay. So the plot of the locus of this p and q, p prime and q prime points, that will give us the stress path. Okay, say for one set of sigma 3 values, we have this circle. For again, we can have one more circle like this, one more circle like this. So if we join all these points, this point again, this point, this that will give us the stress path. It will give us the stress path. Remember that these points are not the tangent points. Okay, these points are not the tangent points. Okay, these points are not the tangent points. These points join the top point of the Mohr circle. Okay, these are not the tangent points. This line does not connect the tangent. This line is not the common tangent. This is something else. The line that is the common tangent, that is what? That is the that will give us the what? It will give us the failure envelope. But this point, this line will give us the stress path. Okay, this line is going to give us the stress path. Okay, understood, right? So for a CD test for NCK, so let us see how we can actually find this. So in stage one is what? Stage one is the first stage, is the consolidation stage. First stage is the consolidation stage. So means what? In the first stage only there will be application of cell pressure. Only there is going to be application of cell pressure. So only sigma 3 is going to exist. So sigma d, that is the deviating stress. There is no deviating stress application, since the deviating stress is 0. So sigma 3 prime equal to sigma 1 prime equal to sigma 3, right? Because we are isotropically consolidating. Okay, isotropically control. So all around we are applying sigma 3 pressure. So with this fact, if we write p prime, p prime is what? Sigma 1 prime plus sigma 3 prime by 2. So sigma 3 prime plus sigma 3 prime by 2 is nothing but sigma 3 prime or sigma 3. Here sigma 3 prime is equal to sigma 3, because what? Because pore water pressure is 0. Excess pore water pressure is 0, because you are allowing drainage to occur. So pore water pressure is 0. Now the q prime part. Q prime is nothing but sigma 1 minus sigma 3 prime by 2. What is sigma 1 prime? Sigma 1 prime is equal to sigma 3 prime, so it will become 0. So this point is will give us the point I. What is the point I? This point I. Okay. Now at some other time. When we start the shearing process and we start the application of the deviatoric stress. When we start the shearing process, when we start and we start the application of deviatory stress. Okay, at that time what we are going to have? So sigma 1 prime is equal to what? Sigma 3 prime plus delta sigma d, because now you are applying this delta sigma d of deviatoric stress. Okay, so that is equal to nothing but sigma 3 plus delta sigma d. Now sigma 3 prime is equal to sigma 3, that is the same. Therefore this p prime is equal to what? Sigma 1 prime plus sigma 3 prime by 2. What is sigma 1 prime? Sigma 1 prime sigma 3. Let me just do it for you here. Me too, right? So what is sigma 1? Sigma 3 plus delta sigma t plus sigma 3 by 2. So sigma 3 plus delta sigma t by 2 is nothing but p prime. Same we are going to have q prime. Going to have q prime equal to delta sigma 3 by d by 2. So now this point is say this one. Okay, now you are seeing that um, this is actually going to have some equal increments of this value, right? That means if we measure the slope of this line or the slope of the stress path id is going to be 45 degree. Okay, this id, the stress path in case of a cd test, is going to be inclined at 45 degree. Okay, this is a fact. For a cd test we are going to have the stress path id inclined at a 45 degree angle. Okay, because with some increment of p, equal increment of q is happening in the vertical direction. With equal increment of p in the horizontal direction, there is a equal increment of q in the vertical direction. Hence we are going to have a line that is inclined to at 45 degree to the horizontal. All right, now, so as I said, this OF prime, OF prime that you see here, this OF prime is nothing but the stress path. This OF prime is nothing but the stress path. So initially as the test progresses, what is going to happen? The circle is going to get bigger and bigger, right? Because you are applying, you are keeping on increasing the, you are increasing the deviatrix stress. Okay, you are increasing the, and finally a stage will come when the soil is going to get soil is going to fail, right? And that circle is this, the failure circle. This is the failure circle, mole circle at failure. So as you see, the stress path actually goes and finally finishes at this point. This point, that point is nothing but the top point of the failure mode circle. Okay, as the stress progresses, our the stress path shows the progress of the test. Okay, the stress path shows the progress of the test. So as you are increasing the deviatrix stress, what is going to happen? The stress path is going up, and finally it's going to end at a point that touches the failure mode circle at the top point. All right, so this OF dash line that passes through this point D, that is nothing but the modified failure envelope or KF line. Okay, this is, if I by mistake I said that, that is the stress path. No, this OF prime, this OF prime is nothing but the modified failure envelope or the KF line. This KF line is inclined at angle alpha with the horizontal. Okay, this is inclined at angle alpha, and above that if you see a line that is tangent to the mode circle at failure, that line is nothing but the failure envelope. This line is nothing but the failure envelope, and below that we have the modified failure envelope or the KF line. Okay, so three things are there. One is the stress path, one is the modified failure envelope, and other is the failure envelope. So modified failure envelope is what you can see here. Okay, modified failure envelope. How can we get the modified failure envelope? If we plot the P prime at failure and q prime at failure for different tests and then join the line, that line will actually give us the modified failure envelope for that soil. Okay, if we plot the p prime at failure and q prime at failure for several tests and then join all these points, we will get a straight line. That line is called the modified failure envelope. Okay, and above that modified failure envelope, that is the failure envelope, that is a tangent to the failure mode circle. So if we derive relation between this failure envelope and the modified failure envelope, what we can do, we can easily construct the modified failure envelope by plotting the p prime final and q prime final, and from there, from the alpha value we can get the phi value, phi prime value, that is the friction angle value. Correct. And these are the two things: modified failure envelope, failure envelope. And the third thing is the stress path. The stress path those for any particular test, as the stress progresses, as you keep on increasing the diabetic stress or the diabetic load over the sample or the axial load over the sample, how is your test actually progressing? That line when you this that line that you get by joining the top points of those intermediate mode circles that keep on that you can draw as test during the progress of the test, during the project, not at the failure, during the progress of the test till the failure point. That will give you the stress path. In case of CD test, that stress path is inclined at an angle of 45 degree with the horizontal. Okay, I hope this is clear. If you have any doubt, you can ask me. So for CD test, so this is nothing but the stress path. Okay, this is nothing but the stress path inclined at 45 degrees, and we are going to have a modified failure envelope that passes through this point D. Okay, and above that we are going to have this failure envelope. Okay, now as we saw this, so as I was saying, if we relate this alpha to this angle phi, we can from alpha we can get phi or we can get otherwise, vice versa we can do that. So in a tau sigma space OF, that is the failure envelope, Mohr Coulomb failure envelope, we can write it as tau is equal to this equation of this line, right? Tau is equal to sigma prime into tan phi prime, and the q prime p prime space OF prime can be written as q prime is equal to p prime tan alpha prime. So this is the equation for the OF prime, that is the kf line. Okay, then if you do some mathematics, if you do some math, you will see that you can get this phi prime is nothing but sine inverse of tan alpha. Okay, this phi prime is nothing but sine inverse of tan alpha. So first say you take this as a sample 1, you test this and it fails at a deviatoric stress of 1 and sigma 3 1. Okay, then we test another sample 2, it fails at df2 when your sigma 3 is increased to 2. Like this you do test, you do some test, CD tests from there. So from here I can get one uh, uh, pf and one qf, and from here you can get and f, right? You can get like this. So this will give you 1 point, this will give you other point, so 1 point, 2 point, like this. One more point you can get like this. So if you join all these lines, you will get a so if it was p sorry p q, right? So plot these points and you get a straight line. So one more test also you can do like this, you can get a straight line, and that angle measure alpha. So from alpha you can directly get phi using this relation. Okay, in case of CD test. Okay, Okay, so let us see. Let us see next. What is there? Yeah. So now let us see the case of our CU test. Okay. Now let us see the case of CU test. Okay. So in CU test, what? In stage one there is application of only the overall cell pressure, right? Cell pressure, we apply cell pressure and we let the soil undergo some consolidation. So in this, so the first stage it's going to be the same. Sigma 1 prime is equal to sigma 3 prime is equal to sigma 3. It is nothing but a cell pressure. So therefore P is going to be sigma 3 and Q prime is to 0, and that is going to give us the point I. It is going to give us the point I. Now in U test, if you remember, we can draw two types of Mohr circle, right? One is the total stress Mohr circle and other is the effective stress Mohr circle. So how to get the effective stress Mohr circle? We just deduct the pore water pressure values from sigma 1 and sigma 3. We get sigma 1 prime and sigma 3 prime. That gives us the effective stress Mohr circle. So drawing that using those values gives us the effective. And otherwise, if we use sigma 1, sigma 3 directly, that will give us the total stress Mohr circle. Okay. So now in stage 2, that is in the shearing stage, let us see. Sigma 1 prime is what? Sigma 3 plus sigma d, delta sigma d, that is the increase in derivative stress, minus delta ud, right? Delta ud is what? Delta ud is the pore water pressure that gets developed due to the application of delta sigma d, correct? Now sigma 3 prime is nothing but sigma 3 minus delta ud. Okay, therefore P is going to be sigma 3 minus delta ud plus sigma d by 2, and sigma Q prime is going to be delta sigma d by 2. So now if we plot that line, these 2 points are going to give us the point U prime. This point is going to give us the U prime. Now again, if we at stage in the second stage only, at some other time again if we measure, it will give us the point U double dash, and then finally it is going to give us the point U, which lies on the which lies on the which lies on the uh, uh, OF prime. Okay, that is the what? That is the what? It is the modified failure envelope, right? It is the modified failure envelope. This is the modified failure envelope or KF line. Right, this is the modified failure envelope or the KF line, isn't it? So here obviously it's going to go and touch that point. Okay. Now for total mode, total stresses, if you want to what to say, uh, if you plot the total stresses, okay, the total stresses if you plot, then you are going to have a line that is line like this. Generally what matters to us, you are plotting the effective stress thing, right? Your p prime and q prime you are plotting, right? So if you plot p prime q prime, what you are going to get, a curved stress path. In case of cu test, you are going to get a curved stress path, okay, like this. So you are going to get a curved stress path. Don't touch there. This curved stress path, this is the for the effective stress. And if you draw the total stress path, this is the effective stress path, ESP, and this is the total stress path. Total stress path means P and Q, not P prime Q prime. You are plotting P and Q. This total stress path will be taken in 45 degree, and this from the total stress path, if we deduct the pore water pressures, you will get the effective stress path, points of the effective stress path. Okay, understood? And okay, you get that right? You understand? So the stress path is curved, which is I u u prime u. This is the stress path, effective stress path in case of our CU test. Now, if you want to plot the effective stress path for both CU and CD test in one plot, you will get something like this. So you are plotting P prime, Q prime. That means this is also ESP, this is also ESP. Right? This is for what? This is for CD test and this is for CU test. Okay. For NC clay. Just a second. So why is this stress path actually very important to us? The reason this stress path concept is very important to us, because it helps us to understand the critical stage solid mechanics. Critical stage soil mechanics. So we are not going to get into this critical stage soil mechanics because it is a higher advanced topic. It is generally taught in postgraduate courses. So this critical state, if you want to understand the critical state soil mechanics, this understanding of stress paths is very important. Okay, so Okay, now what we are going to see is the we are going to deal more with the this Kempton port pressure parameter. So I am not going to go in detail by detail. This all these derivations are actually everything. All these derivations are actually everything is done in the class, right? So I will just go through them a bit slowly to understand what is there. Okay, so here you can see the change in volume by the stress that you are applying. Okay, uh, delta v by v multiplied by 3 means it is the mean means actually there is the this by 3 is down there. Okay, then it is going up, that's why 3 is in the numerator, is equal to 3 into 1 plus twice mu by e. This is nothing but the compressibility of the soil skeleton, and this is a constant. As you can see, this depends upon the Poisson ratio of the soil and the elastic modulus of the soil, right? Now from here what you can add, we can write that change in volume is nothing but v times cv into this cv into this. So we are writing this in terms of the total stress values, prime values we are writing it as a total stress. Also this delta v is nothing but the change in volume of water is equal to nvcw into delta u. All right, all right. From there you can write vcv equal to nvcv. So this derivation I am not going into detail because it has already been taught in the class. Just that you recall this, I have just given it, written it here, so you can just see this whatever it's going through here. You can just see whatever it's written and just recall whatever has been taught in the class. Okay, okay. Now, okay. So this change in volume is written in terms of change in volume of water. Then you are introducing this porosity into volume, right? Porosity into volume, because volume of voids by total volume is what? Is nothing but the porosity. So porosity into volume will give us the volume of voids. In voids, you are considering it is filled with water, right? So N into V into Cw into delta U. So Cw is what? The compressibility of water. Okay, and that into delta U. This is the change in pore water pressure. Okay, so from there we are getting finally this equation. Okay, so in terms of delta V, we are writing this, we are substituting here on the left hand side. Okay, now from here if we write delta u, there is a change in pore water pressure, that is going to 1 plus 1 plus ncw by cv into delta sigma 3 plus delta sigma 1 plus delta sigma 3 by 3. Okay, so this is for conventional triaxial test where delta sigma 2 is equal to delta sigma 3. So here initially we had written this delta sigma 2, right? But in uh, conventional triaxial test, what in conventional triaxial test delta sigma 2 is nothing but equal to delta sigma 3, because in all the directions what delta sigma 2 is delta sigma 3 is the only this cell pressure that is applied, equal cell pressure, isotropic consolidation, isn't it? Okay, from here you can write b is equal to delta sigma 3 plus a into delta sigma 1 minus delta sigma 3. Okay, yeah, right. Delta u1 is equal to b into delta sigma 3 in the first stage that we learned that before. Now delta u2 is equal to a into b, is written as a into b. So from here we are writing, okay, from this equation we are writing this. So this is the delta sigma delta u1, and the other term is the delta u, delta you are writing that at delta u2. Okay, delta u2. Now delta u2 is equal to ab, so a into b you are writing it as a prime, a bar. A bar is equal to delta sigma 1 minus delta sigma 3. So that finally we are having delta u1 plus delta u2 is equal to u. Now for completely saturated soil, water fills the pore space, right? The water will fill all the pore space, and we know the water we are considering incompressible, right? So almost incompressible. So Cw will be much less than Cv. So if Cw is much less than Cv, what will happen? This term, if Cw is much less than Cv, this n into Cw by Cv, that is this term is going to become 0. Therefore this whole term is going to become 1. So we are going to have b is equal to 1. Now for dry soil, air fills the pore space. So for that the compressibility index will be very high, so Cw will be very high. So if Cw is very high, that means what? Cw by Cv will be almost equal to infinity, so b will be becoming 0. Okay, so b will be becoming 0. So this the uh, what to say? Uh, this term we are actually writing as b. Okay. Now B can be measured in EU test in the first stage, as we discussed already in the starting of this class. So B is equal to delta U1 by delta sigma 3. For completely saturated soil sample, B is equal to 1. We saw it here, B is equal to 1. Therefore F prime is going to become A, equal to A. Now what is F prime or A bar? A bar is nothing but delta U2 by delta sigma 1 minus delta sigma 3, measured in the second stage in Cu when sigma 3 is delta sigma 3 is constant. For fully saturated, a prime a equal to a bar is equal to so this one you already can understand, right? So this part I think it should be understandable. Okay, just you are replacing the terms, all the terms. Okay, so this was all about all these things, pore pressure parameters and all this derivation and all you can see in detail in the theory classes. Okay, theory lectures, I remember that this has been taught very clearly and in detail, so I request you to go through that once, all right? Because now if you do start doing that again step by step, it's nothing but a waste of time, right? So let us leave that. So just I put all these things so that you can recall whatever has been taught in the theory class. And now what we can do is that now let us actually start uh, solving the problems slowly. Okay, so let us see the first problem. So an UCS test was conducted on a soft clay in both in situ and remolded samples. Okay, UCS test was conducted on a soft clay in both in situ means so directly without disturbing undisturbed sample. Okay, you are taking undisturbed sample and on that undisturbed sample you are doing the test. And remolded means you just collect the soil and just remold it as a cylinder and then you do the test. That is the remolded sample. So from there we get two sets of data. One set of data is for the in situ sample, another set we get the remolded sample. Now we are to determine the UCS in both soil conditions, also determine the sensitivity of the soil sample. So what is sensitivity? And sensitivity is nothing but, if you remember, UCS of undisturbed by remolded. Okay, UCS of undisturbed soil sample by UCS of remolded soil sample. That is the sensitivity. So sensitivity determines how sensitive the soil is to remolding. Okay, that is what the sensitivity gives. Now this is very easy. Directly all the values are given. Okay, length of sample, initial area, extension of spreading as well as spring constant, axial deformation, everything is given. Just try to find this out. It's very easy. Remember that you need to calculate the corrected area to calculate the stresses. Okay, use the corrected area to calculate the stresses. So try to solve this. This is very easy actually. Just try 2 minutes. Try to solve this one. This one is actually very easy. Directly all the values are given. Just you have to divide the uh, load by the correct area. Corrected area you will get the UCS values. Okay, just do this. I will be back in a minute. Just try to solve this one. So are you very able to solve this? It is very easy, right? I hope all of you were able to solve this. Correct? Just you have to, just the catch is that you have to find out the corrected area. That's the only catch here. Okay, nothing else. That's the only catch. Okay. So first, what shall we do? First, let us calculate the load. So extension of ring at failure is 20 mm and 15 mm. Right. So failure load is equal to 20 into 15 equal to 300 Newton for in situ sample, and is equal to 15 into 15 for remolded sample. Now for in situ, we need to find out what we know the failure load. We can find out the area, corrected area at failure. So area at failure is what? A naught by what is A naught? A naught is given 1500 mm square, so this should be square 1 minus 9 by 150. To calculate this, therefore Q will be 300 by this value. For demolded soil sample, AF is equal to how much? 1500 by 1 minus 20 by 150. Okay, so this one will come around 5. Square, and this one will be therefore sensitivity QU undisturbed by QU remolded. So it is low sensitivity. So if it is between 1 and 2, right? So low sensitive soil. Okay, low sensitive soil. All right. Now let us come to the next problem. A vein 100 mm in dia and 200 mm in height was pressed into soft clay in a borehole. The torque was applied and gradually increased to 100 Newton meter when failure took place. Determine the undrained shear strength. Okay, this is a question of this vein shear test. This is a problem from the vein shear test. So all the problems actually you should solve this by yourself. So these are very easy. Today's problems, these are very easy problems. So here all the dimensions and the torque, everything is given. Just you need to use the correct formula to find out the correct answer. The correct relationship you need to use to find out the correct answer. So just here we need to determine the undrained shear strength, right? We need to find out the undrained shear strength, and from with using vein shear, you know already how to find out the undrained shear strength. So you put the vein shear in the soil and then apply a torque, and that from there you can calculate the UCS, undrained shear strength. So D, this D diameter is given is given. Okay, so this is the relation. So calculate this. Do this math, please. Please calculate. So this is going to come out as 0.02728 is equal to. Okay. Next question is also a similar question. An in situ vein shear test on a saturated clay, a torque of 43 Newton meters were required to shear the soil. The dia of the vein was 50 mm and length 100 mm. Determine the underend shear strength under shear. Okay, the vein was rotated rapidly to cause remolding of the soil. The torque required to shear the soil in a remolded state was 8 Newton meters. Determine the sensitivity. Okay, so again, similar problem, right? Exactly same, just you need to use the same formula again and find the sensitivity at the end. Okay, so calculate the first to find out as for undisturbed, and this just put the values and calculate. Therefore, sensitivity okay, highly sensitive soil, very sensitive soil. All right. Well, it's very sensitive. So generally, this wind shear test is used for these sensitive soils only. Okay, where if you take the soil sample out of that place and do the test, what happens is that uh, the result is not the correct one. Right, so that's why we need to use the vein shear test in situ vein shear test very slowly and very properly, so that we get the correct result. Okay. Okay, let's see the next problem. An embankment 5 meter high. Yeah, an embankment 5 meter high is made up of soil whose effective stress parameters are C prime is equal to 50 kPa and phi prime is equal to 16 degrees and gamma is equal to 16.2 kilonewton per meter cube. Pore pressure parameters are found from triaxial test are A is equal to 0.4 and B is equal to 0.49. Okay, so find shear strength of the soil, the base of the embankment just after the soil has been raised from 5 meter to 8 meters. Assume the dissipation of pore pressure during the stage of construction is negligible and the lateral pressure at any point is half of the vertical pressure. Okay, so many facts are actually given to us. So ultimately what we need to determine is that we need to find out the shear strength of the soil at the base of the embankment just after the soil has been raised from 5 meter, initially it was 5 meters and it was up to 8 meter. So due to this extra increment of stress that is coming in the soil, how much shear strength is there? Okay, we need to find out the shear strength after it has been raised. So what is shear strength? Right, so this is what ultimately we are going to use. Now before that there are some things that we need to see. First thing, there is the play of pore pressure here. So it is written here, the pore pressure parameters are given, and also you can see, assume that the dissipation of pore pressure during the stage of construction is negligible. That means there is no dissipation of pore water pressure. Pore water pressure is there. Pore water pressure exists. So we need to consider the effect of pore water pressure, and that pore water pressure we are going to deduct from the total stress to get the effective stress and then finally calculate the shear strength, because the shear strength is actually a property of the effective stress parameters. Okay, the shear strength is actually the property of the effective stress parameters, right? All these things we have discussed previously, right? Why shear strength is a parameter of effective stress, parameter property of effective stress, you should know that. Okay, now what is a delta u? Right, now delta sigma 1 is what? Increase in vertical stress. So increase in vertical stress, what, 3 meter we are increasing, 3 into 16.2 or 8.6 kb. Now delta sigma 3, lateral stress, so it is given here, assume that the lateral pressure at any point is half of the vertical pressure. Okay, so we got delta sigma 1 and delta sigma 3. Now what we are going to use, we are just directly going to put the values in this equation. Okay, B parameter is 0.49, 24.3, To calculate this, calculate the increase in pore water pressure due to the increase in that extra loading, or due to the increment of that height, this extra pore water pressure is getting generated, right? So the extra 3 meter that you are building, due to the extra building of 3 meter, you are raising the height of the embankment by 3 meters. So with the extra raising of height, you are generating some extra pore water pressure. So that pore water pressure is this. So calculate this, please. Calculate this. So it comes out as 16.67 kPa. 16.67 kPa. Now, what is the particle effective stress? What is the effective stress? Normal effective stress 8 into minus, right? This is the total stress minus the pore water pressure, that is given as the vertical effective stress. Done. So we got this finally. Now you can find out shear stress. This is given as how much? 50. So calculate this. This will give us the final answer. Please calculate 50 plus 112.93 into 10 of 16. This is going to come out as 82.38. Okay. Now next problem. And UCS test. This you should solve. You should be able to solve by yourself. Please. This you should be able to solve. This is very easy and much more similar to what you have solved before. Very easy problem. This you should solve by yourself. So try this. Try to solve. A UCS test was conducted on an undisturbed sample of clay. A sample had a dia of 37.5 mm and it was 80 mm long. A loaded failure measured by the proceeding was 28 newtons and the axial deformation of the sample at failure is 13 mm. Just same as the first problem. We have to determine the undrained shear, unconfined compressive strength, and the undrained shear strength of the clay. So let's please find this out. Very easy. Just find this. Try to find this out. Exactly same. You should be able to do this in just 2 minutes. Very easy. Just put the values and find out. Everything is given. Direct question. Calculate this. What is the QU? QU was what? Unconfined compressive strength, UCS. QU square. And what is your shear strength then? Undrained shear strength then? Undrained shear strength is nothing but okay. Right, very simple. I hope you are able to do that. And I see the next problem. In a CU test on an NC clay, it is a normally consolidated clay. The sample consolidated under a stress of 20 kPa and failed at an additional axial stress of 150 kPa. Okay, sigma 3 and your sigma D is given. Okay, the pore pressure at the failure was 75 kPa. The determine analytically the shear strength parameters of both in terms of effective stress and total stress, means C phi, C prime, phi prime, both, all these four values you need to find out. What are the values of the principal stress ratios, that is sigma 1 by sigma 3? Okay, that you need to find out and calculate the value of the pore water parameter A at failure. All this stuff you need to do. Okay, so let us first write the given data. So what is the data that is given to you? What are all the data that is given to you? Let us write all this thing first, right? So we have failure is 200 kPa, right? And sigma 1 at failure will be what? 200 plus 150. Pore pressure at failure as 75 kPa. So from here I can write sigma 3 prime F So the initial first easy thing that you can directly find out the principal stress ratios. Okay, means sigma 1f plus sigma 3f five m sigma. Okay, now we need to find out the pore pressure. We need to find out the parameters C and phi and C prime and phi prime. All these things we need to find out. Right. So for that we are going to use our basic equation. What was the equation? Right. Right. This is our basic equation from the molecular theory. This was the basic equation. Now can I write this? Can I write this? If yes, why? Can I write this? Can I equate this to this? Yes or no? What do you think? Can I, will I be able to, means, have I written this correct or not? Have I written this correctly or not? If yes, why? So what we did was we put c is equal to 0. Right, so we have made c is equal to 0. So question is, why did we put c is equal to 0? Why did we make c is equal to 0? The answer is in the question. So the question, it is given, this is the CU test on an NC clay. So you should remember, for a normally consolidated clay, the C is always 0 in a CU test. If you recall whatever was taught in the previous class, you will remember that for an NC clay, the C is basically is equal to 0. Right? That's why what we did was we put C. So in the question, the hint is already given to you. Okay, just you need to use the correct information to get the correct result. Okay, so that's why we put c is equal to 0. So from here directly you can put the sigma 1 by sigma 3. Already you have found out 1.75. You put 1.75. From here you can get y is equal to, now similarly therefore yes, what you can see the sigma for NC. That's all. Okay, quite simple. Last part of the question was we have to calculate the value of AF. You need to calculate the value of F. Try to do that. Just try by yourself. How can we find out AF? Just try to do that once by yourself. How to find out what was A? Recall what was A. How we defined A. So A was the change in the ratio of the change in the pore water pressure to the change in the deviatoric stress. Right, right. Increasing pore water pressure to the increasing deviatoric stress, isn't it? So try to use that relation to find out. Just try for once. Just try by yourself a bit. Obviously, I'm going to do that. Just try yourself. Just try a bit. Just try. What is AF? What is A bar? What AF? What is A bar? right? Right? Now, since we can consider that the soil is perfectly saturated, so we can actually write what A bar is equal to A into B. So for saturated we can write B is equal to 1. Right, so this we can write also at A. AF. So what is the increase in pore water pressure at failure? 75. And how is it pore? This is going to get generated. This is going to generate. This is generated due to this additional axial stress of 150 kPa. Right. So right. So you can see this falls in the range 0.5 to 1, okay, which we defined in the first slide. So second slide. Okay. So quite simple, right? So this delta U is nothing but what? Delta U1 plus delta U2. Right, so delta U1 you are considering 0 from first stage. There is no, because consolidation stage there is no pore water pressure that is going to get developed, right? So that is 0. So delta is equal to delta. So that's why you are replacing this delta U2 by directly by delta U. Delta UF. This is nothing but delta U by delta sigma 1 minus delta sigma 3, that you can write like this. At failure you can write like this. Okay. That's all. Very simple. Now see this problem. These are some test data for triaxial CU test that is given. The result of a series of CU tests on undisturbed sample of an overconcentrated clay, whereas below. So test series of test data are given. Cell pressure is given. Debris stress is given. Pore water at failure is given. What three sets of samples that were tested at three different cell pressures? We need to determine the effective shear strength parameters is C prime and pi prime, and also plot the variation of AF with the over consolidation ratio if the pre-consolidation stress is 700 kPa. So over consolidation, so pre-consolidation stress means what? First the soil in the first stage, the soil is consolidated to a stress of 700 kPa. We consolidate it. Then what we do in the shearing stage, just before beginning the shearing stage, what we do, we reduce that cell pressure from 700 kPa to 100 kPa. Then we do the shearing stage. First 100 kPa, then 200, like this. So that is how the soil becomes over consolidated. Right? The soil becomes over consolidated. Okay, so for this over consolidated soil, what we need to do, you need to find out the shear strength parameters, effective shear strength parameters. The test data is given. So what we do first you make a table, a test number, you make test number sigma 3, sigma d, sigma 1, then u, then sigma 3 prime, sigma 1 prime, like this. You make a table first. So first we will make that table. So make that table. Just I will give you 2 minutes. Just try to make that table. We'll just be back in 2 minutes. Just try to make that table first. We'll just make that table that contain the sigma 1 prime and sigma 3 prime values finally, because that value we need to plot the effective Mohr circles. So we'll utilize that value to plot the effective Mohr circles, and then we'll do the common tangent to find the CFI values. Right? So just try to do that first. Just try to do that. I will be back. So, were you able to do that? Yes or no? Were you able to do? So I just told you to write the test numbers. Sorry, just make a table. Finally, okay. So four test. Let me make 4 rows here. Okay. So test 1, 2, 3, 4. The first test cell pressure 100, then 200, 400, 600. Geometric stress at failure 300, 110, 850. Sigma 1F is what? Sigma 3F plus sigma DF. Sigma 1F is sigma 3F plus sigma 1F, right? So just add those. 610, 1010, and 1450. Okay. Pore water pressure 45. You can see the negative pore water pressure values. And then it's becoming positive. So negative pore water pressure values are there initially. That is because the soil is highly over consolidated at the beginning. That's why there is a dilation. So the soil tends to generate negative pore water pressure, because if in CU test, remember in second stage, in CU test, remember there is drainage valve is closed. That means you are not allowing any volume change to occur. But There's a tendency for the volume to what? Volume to increase. That's why, that's why it generates negative pore water pressure. As negative pore water pressures are generated, as negative pore water pressures are generated, we are getting negative values for highly organized. As the soil tends goes near the normally consolidation part, as it goes near the 700, the pre-consolidation state, so this pore water pressure changes to positive. Okay, sigma 3f 100 minus of minus 45, 200 minus of minus 15, 400 minus 50, and 600 minus 110. Similarly, 400 minus of minus 45, 610 minus of minus 15, 1010 minus 50, 1450 minus 110. So this is what we get. Then what we do, then we use this value sigma 1 prime f and sigma 3 prime f, these two values to plot 4 Mohr circles. So see, you can take the radius sigma 1, sigma 3 and sigma, you can plot 4 Mohr circles. After drawing 4 Mohr circles, what we do, we draw a common tangent to this circle. So you can see that tangent will actually give you the failure envelope. You can see here for you all these circles, 4 circles, 1, 2, 3, 4 are drawn, and on drawing these 4 circles, where we can get a common tangent, and that common tangent has an inclination of 25 degrees. That is the, it will give you the friction angle of the soil, and the intercept is the, will give you the cohesion of the soil. So finally from here we can get, so try to plot this one using a graph paper. Okay, try to plot this thing by yourself, plot all the values by yourself using graph paper, and check whether you are getting the circles or not, whether you are able to draw the uh, this tangent line or not, common tangent line or not. Okay, do this by yourself, repeat this problem by yourself, do this by yourself, and try to see if you are getting the same values or not. Okay, because when you draw this by yourself in graph paper, things tend to change. All right, things tend to change. That's why I am saying, repeating again and again, that please try to solve. Now, the second part of the problem is plot the variation of AF with OCR. AF with OCR. Now what is AF? Right? So just I will write sigma 3, make a table sigma 3 OCR AF. Now first, what is the sigma 3? 100. Right? For 100, tell me what will be the OCR for this first test. What is the OCR? What is over consolidation ratio? What is over consolidation ratio? The pre-consolidation stress by the present stress, that is 700 by 100. 700, it will give you 7. What will be the AF? Is delta UF by delta sigma DF. DF. So minus 45 divided by 300, that will give us minus 0.15. Minus 45 divided by 300 minus 0.1. Okay, now again you can plot for 200. OCR will be what? 200, 700 by 200. So 3.5. This will be what? This will be minus 15 divided by 410. Minus 15 divided by 410. It will give us minus 0.03. Next is 400. 700 by 400.75, and 50 divided by, now it's coming positive, so 50 divided by 610, 0.082. Okay, and the last is for 600. 600 by 700, 1.2, 700 by 600 1.2, and from here 110 divided by 850 is 0.13, and let me do 850.13. Okay, done. Now what we have to do, we are asked to plot the variation between OCR and AF. So 0 AF, this is a positive side, this is negative side. Okay, so initially 0.13, from 0.13 it is going with this, like this, like this, like this. So this is minus 0.2 to 0.222, we'll get something like this. Okay, so this one 0.13, this is at OCR of 7, this is at OCR of 1.2. So you can see at this point it's crossing the axis, because at this point the soil is because it is going towards normally consolidation. Okay, that's why our AF is becoming from negative, it's becoming positive. Okay, okay. So for normally consolidated, A is between 0.5 to 1, and for over consolidated 0.5 to 0, sorry, to 0. So at these stages it's neither fully over consolidated, neither fully normally consolidated, it's something between, in between normally consolidated and over consolidated. Okay, okay. So let us see where is the problem. Yeah, this problem, right? Yeah. So a compacted soil was tested in an undrained triaxial test using a cell pressure of 400 kPa. Before the application of shell pressure, the pore water pressure in the sample was 0. Okay. So as strain increases, the electric stress is increasing obviously, and you are seeing that pore water pressure is, so pore water pressure is getting reduced. So yeah. So what we are asked, determine B. What was the soil completely saturated? Plot the deviatoric stress with strain. Plot A with strain. Okay, so let us do step by step. First question is determine B. So B is determined in the first stage. In the first stage, how do you determine? Change in pore water pressure by changing the cell pressure, right? So initially, when there was no deviatory stress, the pore water pressure was 250, and what was the cell pressure? The cell pressure was 400. So from there we can find out, right? Using these two values, we can find out. So B was, we write it here only. So B was 250 by 400. So it will be 0.625. It is much less than 1, not even close, not even 0.959 like this, right? Not even close to 1. So that's why we can say that the soil was not completely saturated. The soil wasn't completely saturated, right? So undrained test is done. Okay, undrained test we are doing. Okay, now the second is plot deviatoric stress with strain. That you can do easily. You have strain, you have deviatoric stress, you can plot this value, you can plot the value, that you can do by yourself. Okay, so please use graph paper, or at least use Excel to plot this. See how the how it is coming, how the graph is coming. Just try to solve it. Okay, try to plot this. Okay, now let us come to plot A with strain. So we have to plot A is what? A is nothing but our pore pressure parameter, right? So for that we will make a table. So first is the strain, then we have this rigid pore water pressure in the second stage, then we have the deviatoric, then we have A bar. A bar is what? Delta U2 by delta sigma D. Okay, and then we can have A. A is what? A bar by B, because A bar is A into B. A bar by B is equal to A bar by 0.625, right? We can find A from here. Now we cannot put A bar is equal to A because B you already saw that B is not equal to 1. So you have to use this. Let us do this. So I'm just writing whatever value, whatever is there. Okay, whatever value is there, all this I'm just copying these values. Okay. Last we have, all right. So A bar is what? So A bar is due to this by this 35 by 570. 35 divided by 570. 35 divided by 570 is 0.61. Next we have minus 100, 100 minus 100 divided by 950 by 950 minus 0.105. Then minus 148 divided by 1100, we'll have minus 0.132, 0.152. Similarly, sorry, excuse me. After that, we can divide A bar by 0.625 to get A. 0.097. Okay, now what we can do? Now we can plot. Okay, you can plot the A value with strain. So A value with strain you can plot, you will get a something like this. Okay, A strain you can plot, you will get something like this. So do this, plot this by yourself. Okay, plot this by yourself. Wait. This is problem. This is problem. Okay, that's problem. So in a triaxial test, a soil sample was consolidated under a cell pressure of 700 kPa and back pressure of 350 kPa. Thereafter, with drainage not allowed, the cell pressure was raised to 100 kPa, resulting in the increasing pore pressure to 445. The axial load was increased to give a deviatrix of 575, this is 800, okay, and the pore pressure to 640. With the pore pressure, okay, A and B you need to find it. Okay, slowly we will do. First, let us calculate B parameter, which comes from the first stage. So, what is B parameter? Right, this is the B parameter. So it is given A soil sample was consolidated under a cell pressure of 700 kPa and a back pressure of 350 kPa. Thereafter, not allowed, the cell pressure was raised to 800 kPa, resulting in the pore water pressure reading of 445 kPa. Right? So that means initially when 700, that time the pore water pressure was 850. Back pressure is applied equivalent to the pore water pressure. So 700. So our this one is 445 minus 350. And what is the increase in the sigma 3? That is 800 minus 700. This will give us B. 95. So very close to 1. It's almost saturated, right? Almost saturated. Now, the second part is to find out A. Yeah. For that, see, first sigma 1 in the first stage, sigma 1 is equal to sigma 3 is equal to 800, right? 800. Then you start sharing. When you start sharing, it is going to be sigma 3 plus 575, right? So 1375. Now what is A bar? A bar is, so delta U2 is what? 640 minus 445. Okay, and delta sigma T is nothing but 1375. This what to say, this delta sigma D is what? Delta sigma D is this one, 575. Get 0.339. For A is equal to A bar by P. Okay, hope you got that. All right, very simple. Let's go to the last problem. A sheet triaxial test on a saturated clay sample give the following results. Cell pressure is given, debiting for water pressure. More cells. Okay, so you need to do it by two methods. First, so now it's not possible for me to draw the mode circle using graph, pen, and paper, right? So what I suggest, you draw this, you solve this problem yourself, and you will see that things are getting clear. Okay, how to do? So same sigma 3 I know, sigma D I know, sigma 1 I can get, U I know, sigma 3 dash I can get, sigma 1 dash I can get. So also I can get P dash, P prime, P prime. So 150, 102, 150 plus 102, 252, 80, 150 minus 80, 70, 252 minus 80, 172. P, P prime, sigma 1 prime plus sigma 3 prime by 2, 51, sigma 1 prime minus sigma 3 prime by 2, 21. Like this, similarly, you can do. Okay, what is P prime? 300, 200. Okay, now what we can do, we can solve this by two methods. One is the normal, you can plot the mode circles and find out the phi and c. So other method will be to plot the p prime, q prime. So we will get something like this. We get this alpha prime is equal to 23 degrees. From here we can get minus 25 degree. Okay, so like this you can get. So so for this the c is equal to 0, but let me give you the relation. Say you have p prime q prime, say you have some intercept a, and you have this alpha, this is a kf line. So from here we can get c prime is equal to a prime by not a prime a by cos phi, where phi is equal to sine inverse. Okay, so this is how we can get from this we can remember. Okay, so try to do this by yourselves and find the do this by yourself in graph paper. Take graph paper, take proper scale and draw these circles, draw these plots, and see whether you are getting these values or not. Okay, so with this we will end today's session. I hope everything was clear to you. If you have any doubt, please feel free to contact me. And our next session will be on 29th February. That is the Good Friday day. 29th February we are going to have the next session from same time 6 p.m. to 8 p.m. 29th February Friday, 29th March, sorry, 29th March Friday from 6 p.m. to 8 p.m. Let us meet again. So thank you so much for attending to this session. So if you have any doubt, please feel free to contact me anytime. I will be available over email anytime to address your concerns. So thank you so much for attending. So see you on 29th March Friday 6 p.m. to 8 p.m. Thank you.